First of all, I would like to thank Sikkim University and Physics Department of Namjib Government College for providing me the opportunity to make a practical work on physics for our third semester. I would also like to thank our respected Sir Dr. C.P. Khatiora for giving me the chance to make a video on the topic parallel and perpendicular theorem for moment of inertia. My name is Palpal Rai, bearing roll number 19NS0008 from third semester. So, firstly, let us talk about the moment of inertia, the definition of moment of inertia. So, the definition is a quantity expressing a body tendency to resist angular acceleration, which is the sum of the product of the mass of each particle in the body with the square of its distance from the axis of rotation. So we are going to talk about the um, definition of perpendicular axis theorem. So what is the perpendicular axis theorem? So let us start with the formula. I z axis equals to I x axis plus I y axis, which we will discuss later in the numericals. So it defines is the definition of this perpendicular axis theorem is the moment of inertia of a plane laminar. So what do we mean by laminar? Is the 2D shape. So we should not talk about the 3D, but we should talk about only the 2D here. Body about an axis perpendicular to the plane is equal to the sum of the moment of inertia about two mutually perpendicular axis have a common uh, common point of intersection. So what do we mean by this definition is the moment of inertia of a plane laminar body about an axis perpendicular to the plane is equal to the sum of the moment of inertia about two mutually perpendicular axes have a common point of intersection is given by this formula. So the moment of inertia of a plane laminar body about an axis perpendicular to the plane. So Iz is perpendicular plane, which is equals to Ix, means mutually perpendicular. The two mutually perpendicular. So Iz equal to Ix plus Iy. So both are mutually perpendicular. So next we will talk about the parallel axis theorem, the definition of parallel axis theorem. So parallel axis theorem. the moment of inertia of a body about any axis is equal to the sum of its moment of inertia about a parallel axis through its center of gravity, or we can say it is a mass, and the product of the mass God goes some mobiles mass of the body and the square of the distance between the two axes. So we can numerically write it as I equals to ICM, which means center of mass plus m a square, which is the summation. We can also write summation n small letter m, which is converted into m. This is the summation of small mass. Okay, so the definition is the moment of inertia of a body about any axis is equal to the sum of its moment of inertia about a parallel axis through its center of gravity and the product of mass of the body and the square of the distance between the two axes. So we will discuss it in the later numericals. So let us prove the perpendicular axis theorem. So perpendicular axis theorem. So the formula of perpendicular axis theorem is Iz equals to Ix plus Iy. So let us prove this formula. So here is a plate, 2D plate, and let us mark our axis. This is the center, and let us mark the axis. This is y-axis, which is going through the plate, which means this is this aligns this y-axis and x-axis aligns with the plate. So x, y. So these both are perpendicular, which is 90 degree to each other. So the z-axis will go through this plate, 2D plate. Remember that this 2D plate has no thickness, zero thickness. Let's assume that, and this is the perpendicular, and so the condition here is, the conditions we should consider is Number 1, x comma y comma z should be mutually perpendicular. What does it mean? So this x axis, y axis and z axis should be mutually perpendicular, which means it should form 90 degree to with every axis should form 90 degree with each other. So from number 2, x and y axis should be in the plane of the body. So x and y should be in the body, but should align in the plane of the body, but the z-axis should pierce through it, so it doesn't align with the body, unlike x and y. So number 3, z should be perpendicular to the plane of body. So as said earlier, the z axis is perpendicular to the plane of the body. So let us consider a small mass dm right here, and let's join this. So let's name this point as x and y. So by differentiating, let us put d, because it is the small mass. D I x equals to d m y square. So dix equals to dm y square. Dm y square, where this y square come from? This come from here, y and y. This y and y combine, it becomes y square. So this is x and x. So similarly, diy equals to dm x square. These are the, because of this 2x, it becomes dm x square. So what about this z axis? So z axis, d I z equals to dm. So let us name this distance equals to r. So by Pythagoras theorem, r equal to x plus y. Okay, so dm r square, which we can further elaborate as dm x square plus y square. So x square plus y. So we will multiply dm and x square plus y square. So dm x square plus dm y square. So di square equal to dm x square plus dm y square, which was obtained earlier. So we can add this here. We can integrate this, and so by integrating we get the formula iz equals to I from y squares y axis plus I axis. So we got the formula here. which proves the theorem of the parallel perpendicular axis theorem. Now let's prove the parallel axis theorem. So let us consider a plane. In the center here, let us draw a perpendicular axis which go through this plane and a perpendicular here axis here. So in this parallel axis theorem, center of mass is really important here. So the formula is I, moment of inertia equal to ICOM. It means center of mass plus mass A square. So this is the formula. So let us see some conditions. Number 1, two axes must be parallel. Number 2, so these two axes must be parallel to each other. And number 2, one axis should pass through center of mass. So as you can see here, this is center of mass, COM. Let us denote this point as center of mass. So one axis should pass through center of mass. So this axis is passing through center of mass. So number 3, let us name this distance as A. So A equals to perpendicular distance between two axes. So as you can see, this aligns in the plane and this is going through the plane. So this becomes parallel to perpendicular distance to each other. So let us name this I, center of mass, and let us denote this with I. So proof. So this, let us differentiate. First, let us consider a small mass m dm right here, and the distance between dm and center of mass, let us call it r. Then d I c o m equals to d m r square. So this moment of inertia of this line, this point, is dm r square. So r square is the radius, not radius but the length. So di, this di equals to dm r plus a whole square. So r plus a whole square, because a and r, from this point to this point, this is a distance of a plus r whole square. So Let's elaborate this. dm square plus dm to ra. So a square plus b square plus 2ab which is multiplied by dm. So let us integrate it. So this equals to this, so we can write di come here plus dm square. Let's copy this here plus dm to ra. So by integrating di we get I equals to ICOM plus A is constant, and dm, if we integrate int, we will get m. So this m is the whole space, m a square plus 2a is constant, and let us leave here with integration dmr. So this dmr equals to 0, so I equals to ICOM plus m a square. We can also write it as I equals to ICM plus summation of small letter m a square. This is the summation of m. So we can this is the real formula, hence proved.